Okay, so good morning, everybody. It is not a wrong lecture title, so I just had this in mind, and the other one was just a preliminary. So we are just continuing the same line, don't worry. So yesterday, I ended up with a question, what is the standard model? And today I'm going to try to address this question. So what the standard model is? This is a model, a framework which utilizes quantum field theory, which we briefly discussed yesterday. And its most important feature is that it unifies electromagnetic and weak interactions into a single electroweak interaction. And also it places electromagnetic or electroweak and strong interaction in the same context. The unification is actually quite artificial, but it is the basis of our understanding. And this theory, it is a very modest name. It's called model, but this is just a really modest name. Steven Weinberg was confessing later that because of modesty, he just named his theory a model. Actually, this is a theory which describes most successfully all our world except dark matter and dark energy. And it has some key non-trivial ingredients inside. So one is local symmetries, which predict non-trivial interactions of quantum fields. And another is spontaneous symmetry breaking. So you have two conflicting ideas. You impose some symmetry, and then you break some of the symmetry. And on the basis of these conflicting ideas, a new theory appeared, which really explains our world. And also it has some quantum anomalies, which I don't have time, which is a really loving and interesting subject, but I don't have time to discuss today, which break some classical conservation laws in the quantum theory. And the Higgs field, which is essential for this theory, was a central topic in particle physics for 45 years or so. So now let me try to discuss this from different angles. So first angle is just writing some equation. And so there is this very compact basic equation, which is the Lagrangian. And as I said yesterday, if you know the Lagrangian, then you know everything, because other things are just mathematical rules which follows from this Lagrangian. And here, this has this kind of nice Lagrangian, which can be written just in 3 rows. And in principle, this means that it can be printed out on your T-shirt, and it looks pretty easy if you know already everything. If you don't know, maybe it looks a little bit complicated. But I'm not going to discuss any of these symbols whatsoever, so don't worry. This is just to show you that there are different approaches how you can explain this subject. So theorists like to discuss this way. But then if you unpack this compact equation, then you get something like that. So actually, this is a very, very long list of the same equation, which is just unpacked. We can wait for maybe a few minutes before it ends up, but actually, I'm not going to do this. So you can actually describe pretty the same information in form of pictures. These are Feynman diagrams shown on the left. These Feynman diagrams actually encode exactly the same things which are shown on the equations which are scrolled on the right side. But certainly, this is much more compact, easier to understand, and easier to manipulate with. And there was a very famous story about Feynman and his kind of discovery of these Feynman diagrams, when at one of the conferences, one fellow presented a talk showing that 2 theories which seemed to be equivalent after his calculation showed up to be not really equivalent. And then Feynman was kind of thinking about this problem, and then the next day, actually, the talk was at the evening, and the next morning, Feynman came to this guy and said, yeah, you're right. So yesterday I cross-checked your calculations, and you're right. And so the other fellow was really surprised because he spent half a year to make this calculation, and Feynman managed this just in one evening. And so the reason is that Feynman used these Feynman diagrams, which are really much simpler and quicker way to arrive to the final answer. But we're not going to discuss the diagrams neither. So I just try to address the standard model from really distinct angle. So first I want to discuss the idea of unity of phenomena, why we are searching for this unity. The answer is kind of very simple. When you try to unify different phenomena, you try to actually understand them deeper. And a great example of that is electromagnetic theory. So before Maxwell, we had really lots of information about electric field, magnetic fields, and various counterparts. And then Maxwell showed up that actually electric and magnetic fields, they are very coupled together. And he unified them in a single electromagnetic interaction. So instead of having separate electric and magnetic forces, we have just electromagnetic force. And the electromagnetic field is a unique object. A very, I think, a nice and insightful example how you can demonstrate this is so-called Einstein Paradox. In general, thinking about different paradoxes is very useful because when you really find a paradox and try to resolve it, you usually get deeper understanding. So Einstein Paradox is the following. So imagine you have some magnet and you have some charged particle moving close to this magnet with certain speed. Then you know that there is a Lorentz force acting on this particle, which is just proportional to the vector product of the speed of the particle and the magnetic field. But now let's go in a rest frame of this particle. So let's change the framework or the system and write with the particle, and certainly in this system, the speed of particle equals to 0, right? And so now you ask yourself, so in this system, what is the force acting on this particle? According to this equation, it should be 0. But according to the previous one, it is not. So if changing the coordinate system, you really come to different physical output? Certainly not. And the explanation of this paradox is that, by the way, what is the explanation? Maybe anybody knows? Please raise your hands, students. No, not Gorbunov or Akhmedov. Certainly you know. You teach this. Okay, please.
So, if I remember right, we need to calculate the change of both fields when we change the Lorentz frame. And there is an electric field will be here.
That's right.
Instead of
Right. Very good. So, you see, young gentlemen made a really right answer. So electric and magnetic fields are not something solid. They just depend on the coordinate system. So if you change the coordinate system or you make a boost, then the fields also change. And this is a cartoon which explains that. So if you have a boy with some charge around, electric charge, so and he sees just electric field, and then if there is a girl, maybe his supervisor, moving around, always busy, so you see with a laptop, and so she's just cross-checking what he measured, but then she actually sees a much more complicated picture in her frame. So she sees an electric field, which is, as you can see, condensed in the orthogonal plane, and also a new electromagnetic field, magnetic field which appears. And when you calculate forces in her system and forces in his system, then they get in agreement. Right. And so now we're trying to discuss how to unify electromagnetic force and the weak force. And at first glance, this looks nearly impossible because these forces are really very different. let's see into this table. So we can compare range, so what is the typical distance where force has any value. So for the electromagnetic, this is infinitely long range. And for weak interactions, we know that this is something like 10 to the minus 18 meters. How do we know this? So here we have two margin nodes. So we can estimate the mass of the carrier, which is about 100 giga-electron-volt. And from this mass, inverse of this mass is the range. So if you use the same equation which I showed you yesterday, you can arrive yourself to this conclusion. So 10 to the minus 18. So the carrier mass for the electromagnetic field, electromagnetic interaction is 0, and it is very heavy for weak. So also parity is not conserved in weak interaction, and it is conserved in electromagnetic interaction. And also particle identity after the interaction, electromagnetic conserves this, and the weak interactions in general does not conserve this. So this look really as very, very different interactions. So how we can try to unify this. And before answering this question, we should ask ourselves, but how in general can we even approach to make any theory when you don't have any classical analogy for that? And actually, this is not that simple question, because let me remind you how we constructed electromagnetic interactions in its quantum version. So the story is the following. So first, James Clerk Maxwell created a theory, as I just mentioned, of electromagnetic interactions. Then it was turned out that his theory is incompatible with Galilean transformations, but turns out occasionally, so he did not assume this, that it turns out that his theory occasionally was invariant under Lorentz transformation, which appeared later after his theory. This is kind of very unexpected. But then this led to the following, that instead of considering independent electric and magnetic fields, you can introduce a single electromagnetic field, which should be transforming correctly under Lorentz transformations. And then there is another piece of instrumentation. This is so-called principle of least action or minimum action. Actually, it is not minimum. It can be minimum or maximum, correctly to say least action, which suggests a recipe. If you have a free theory in which you have this partial derivative, you could replace it by so-called covariant derivative, which is a capital D, which is just sum up of this partial derivative multiplied by imaginary I plus Q multiplied by A mu, where A mu is the electromagnetic potential. It just follows from a math from the least action principle. And then when you do this, then you immediately recognize that after this replacement, you again have a free theory. So free theory can be constructed just with this replacement. But you can then read this backward. You start with free theory, make this replacement, and you get the interaction theory. And this is the receipt, actually, which is literally used in quantum field theory to construct quantum electrodynamics. So how it works in practice, you take the Lagrangian like that, where you have this partial derivative here. You make this replacement. So instead this partial derivative, you take the covariant derivative, and you just split this this Lagrangian into two parts. The first part is, again, the free Lagrangian, and the second part is the interaction Lagrangian, where fermions, their current in particular, interact with electromagnetic field. And you are done. All the rest is just a mathematical set of rules, how you can deduce from this Lagrangian Feynman rules, make cross-section calculations, and so on. Now, I'm still asking a question how we can construct a theory of some other interaction, like strong interaction or weak interaction, for which we do not have any Maxwell-like classical equation. So we don't have this simple recipe which follows from principle of least action. And before I give you an answer which is currently considered as a kind of a right answer, which can be also wrong at some point, let me tell you kind of a story with 3 friends, physicists. It is a totally imaginary story. It never happened. But this is just something which can help us to come up to the right point. So imagine you have 3 friends. One is theorist and 2 are experimentalists. And they are sitting together in a bar discussing something. And so a theorist says, we need to know the electron field in 2 very distinct astrophysically separated points. And so you should go both to these points and measure the field. And remember, he says, that the phase of the electron field is just a convention if it is a constant. So don't care about that. So you can choose it arbitrarily at any point. And so after drinking some beer, 2 experimentalists fly to the very distant destinations, X and Y, with only one-way communication, because they were lacking some money for better communication. They spend it to beer. So this is what happens. So they go to these distinct points to measure the fermion field. And then there was a problem. Then they measured the electron field at points X and Y and send the result back to the theorist. But they all forgot, you remember that they were drinking, they all forgot to agree on the phase convention. So what should be chosen as phase? They agreed that it is arbitrarily, but they forgot to agree arbitrarily equal to what. And so when a theorist received 2 numbers from these points, X and Y, he finally realized that he cannot do anything with that, because first idea was that he could compare these 2 fields, psi of X minus psi of Y, but then he remembers that maybe they chosen some phase, alpha in point X, and then there is this phase factor here, and alpha at points Y, and then there is this exponential for the field in the Y place. And I think everyone can understand, even if you are not very friendly with mathematics, that this difference and this difference, these are totally different things, right? So they're just dependent on this alpha. And so he realized that he could not do anything with this. So not knowing exactly what is alpha of X and alpha of Y, the theorist cannot compare the 2 numbers. And then, only after that, he began to think deeper. He realized that actually, there is a problem which is even worse than that. He could probably not send his friends to very distinct astrophysical places. He could take instead just very close points in space. And if you cannot calculate, if you don't know the agreed phase factor, then you simply cannot compute a derivative. Because in order to calculate the derivative in a point, you have to know the phase at point X and the phase at point X plus delta X, and take delta X to 0. But if you cannot calculate a derivative, then what kind of sense any free theory has? Because any free theory has a derivative in the equations. So then you have a really big issue that a free theory is actually not valid mathematically. It is an ill-posed problem because of the phase convention. And only after that, this imaginary theorist came to another idea. He said that we have to find a way how to formulate a theory which should not really depend on the phase convention in any point in space and time. And so he again looked for the free Lagrangian, and you can immediately recognize that a free Lagrangian is not invariant when you make this transformation, when you take, instead of field psi, field exponential with some factor here multiplied by this field. Because you have this derivative term, you, after this transformation, obtain the same Lagrangian minus this new term which appears. So 3 Lagrangian is certainly not a good object because it is certainly violating his wish to construct a theory which should not depend on the phase convention. But then he found that if you take another Lagrangian, which looks a little bit more complicated, so it is the same 3 Lagrangian here, minus this new term, and minus some factor here. I will explain it later what it is. And then if you are doing simultaneously 2 transformations, you transform a fermionic field like that, and simultaneously you transform the electromagnetic field like that, then this Lagrangian is now the invariant one. So you can take whatever alpha of x, it can be arbitrarily function, but then this Lagrangian is really invariant. And this is exactly quantum electrodynamics Lagrangian. So what is F mu here? This is so-called electromagnetic tensor, which turned out to be also invariant under this transformation of the field. As a bonus, after this approach, a theorist automatically obtained that mass of this field, A, should be 0, because if he would introduce this mass term back to this Lagrangian, then immediately you can see that when you do this transformation of the fields, this mass term is not invariant. So you get some 4 pieces, and they are not compactified back to the product of A prime, A prime. And the only way out is to impose that the mass of this field A should be 0. So for the electrodynamics, this is really a great success. You do not assume that it is 0. It just follows from this new principle, a principle that a theory should be invariant under this phase transformation. Theoretically, this is called gauge transformation. And let me give you an animation which shows that this is not only math, but also there is a very clear picture behind that. Let me explain what this animation is showing. Initially, I have an electron which is at rest. And I draw, for the first 2 seconds, its electric field. This is just a uniform electric field. And then I suddenly give a kick to this electron. So I very quickly accelerate it to this certain speed. And afterwards, the electron moves with a relativistic speed. And you can see, this is just exact equations, by the way. So it's not just ad hoc construction. So you immediately see that when the electron was kicked out to the new position in just 0 time, the field around is very different. The electric field is compactified in the orthogonal plane if it moves with the relativistic speed. And the electric field should be a continuous set of lines at every point. And in order to merge these 2 pictures, the only way out is that you can see the circle. Can you recognize what this circle means? What do you think it is? Нет. Very close. This is electromagnetic wave, which is just propagating. So you just created a new object which is independent. So before that, we just had a set of mathematical equations with some kind of maybe idea how we should arrive to this Lagrange and so on. But now we can see that this A is not just a mathematical object. This is something really which can live independently of electron. Because now when you have this wave, it just goes away, forgets about an electron, and you can detect this wave maybe 100 kilometers away from here. So this is independent physical object. And this just follows from actually a very classical consideration. So what this example shows that an electron by itself is not well-defined object. It is defined object when you only have around an electromagnetic field. And these are independent fields, but they are interacting. Okay, so I hope that now you understand better this animation.
And what is the point, white points, around electrons?
White points? You mean this?
Yes.
These are arrows. Arrows. Because you have an electron, and so arrows point to the electron always. Okay, makes sense? Okay, and let me give you just one example how you can apply this principle to construct a new interaction. Because so far, I hope it was quite nice, but we kind of just reconstructed already known things. So we could construct quantum electrodynamics from the other thing, from the other angle, but now we just follow it a new approach from gauge invariance principle. But in order any principle to be useful, we have to provide something new, which was not present on the market before. And let me give you just a single example. There are many examples of that, and the standard model is another one. But I want to consider so-called scalar electrodynamics, when I forget about the spin of an electron and consider that an electron is just a spinless particle. So how we can apply this principle to understand how the scalar electron can interact with the electromagnetic field. So what you do, you again, this is a recipe. You take a free Lagrangian. This is the kinetic term together with this second term for the scalar field. And this is a kinetic term for the electromagnetic field. So these two fields do not interact. And now we can, first of all, let us ask ourselves, try to think how a scalar should interact with electromagnetic field. Maybe you remember from the last slide that an electron which has a spin has a current, and this current interacts directly with the electromagnetic field. So you can maybe assume that also you can construct a current out of a scalar field and make it interacting. But would it be a right theory or not? Let's see. So the recipe which I gave you is very simple. You just replace a partial derivative d mu by this covariant derivative, which is this guy here. So very simple. You just come from this Lagrangian to this Lagrangian. You just replace d small by d capital, right? And then you just unpack this. You unpack this and you get these four terms. So you get again a free Lagrangian, and then you have these pretty complicated things. But in these two, you can really realize that this is again a current multiplied by the electromagnetic field, pretty similar to what we had for spin 1/2 fermion. But then there is something unexpected. So there is this fourth term which couples two scalar fields and two electromagnetic fields in single point. So it turns out that a scalar electron would interact more in a more complicated way with respect to 1/2 spin fermion. This might be wrong if you cross-check this with an experiment, but so far this principle was proven to be correct. So the gauge invariance predicts the interaction between this field phi and electromagnetic field. And this is pretty nice because now we have a new way how we can construct a theory. So we will find some theory, we'll impose some symmetry, and then we'll replace this partial derivative with covariant derivative, and we'll get a new interaction theory. To this point, I expected that you are tired of equations. And so we're going to have a small pause. You can enjoy this cat, which is also overwhelmed like you by lots of equations. So please refresh your memory, and we'll continue half an hour later. Are you okay? Feel better? Okay, now go to the second part. So the algorithm which I provide. The gauge invariant is now a method for the prediction of interactions. And the algorithm is very simple. You take a free theory, you replace the partial derivative by a covariant derivative, you introduce a compensating field A with index I, which means that there may be different fields like that, for each generator of the symmetry group in your free theory. So far we were considering just a very simple case, but you can create your theory not with a single field, but with many fields, like they can be organized in doublet, triplet, or whatsoever. If you organize them in doublets, for example, you will get something like a standard model. If you organize them in triplets, you will get quantum chromodynamics, and so on and so forth. If you organize them in 5 multiplets, then you will get, or 10 multiplets, then you get SU5 or some other grand unification model mentioned yesterday by Professor Zhizhong Xin. So, and then you introduce for each of these fields its own tensor, which should be analog of the electromagnetic tensor and should be gauge invariant Lagrangian for these new fields. And then the interaction is no longer optional. So you just automatically get a theory with the interaction. And you just have a systematic way. You check this new theory with data, and you roll out this theory if it violates data, or you say that the theory is not ruled out. By the way, you never can say that the theory is right. Theory with respect to the experiment is always in a slave position. So it can always be ruled out, but it can never be proven to be right. Theory is always in the situation where it is still not ruled out. This is the situation for standard model, for example. It is still not ruled out. So, and if there is somebody who created this for the first place, yes, it was not me, and it was not that theorist with two experimentalists. It was two theorists. To my knowledge, maybe I'm wrong, maybe Professor Sinjo knows this better, but to my knowledge, these were Salam, Abdus Salam, and John Ward, who back to 1961 suggested for the first time that maybe if symmetries gives conservation laws, then maybe the interactions also can follow from symmetries. And so for the first time, they introduced this idea that from imposing symmetries and requiring gauge invariance, you can create the interaction theory. So now let me go to the standard model. It has the following pillars. First, it has a certain symmetry. As I said to you, now the idea, this is just technical detail, so you have to find a right symmetry for which you will introduce a right number of compensating fields, which should compensate these phase transformations. And then you check this theory with the data, and if you are lucky, then this theory is considered as okay. And a standard model in particular relies on a very weird looking theory for the first time. So this is SU2, which we know, I think, everyone, because we studied SU2 for spin 1/2 electron in quantum mechanics. But this SU2 is not for spin, but for left chiral fermions, which are massless in this theory. I will talk on that later. And then multiplied by U1, so far we just consider it scalar electrodynamics or quantum electrodynamics. These are all just examples of U1. So when you just have a single generator, which is just a number, which is just a charge. But this U1 is with some label here, Y, which means a hypercharge. Whatsoever does it mean, doesn't care for the moment. But what is important is that you impose this symmetry based on some clever ideas. As I mentioned yesterday, one of them was that weak interactions violate parity, and this is why you have this symbol L here. And then you know that electron and neutrino should be in a single multiplet in order to interact with charged lepton, charged W, because it transforms one to another. And then you have somehow to unify this weak interaction with the electromagnetic interaction, and so you just add another symmetry in order to have 4 generators. because we should restore 2W, 1Z, and 1 electromagnetic field. And so you have this kind of symmetric theory, so like this butterfly which has symmetric wings. But as I said earlier, any gauge invariant theory predict that all gauge bosons should be massless. And therefore, this theory also predicts immediately at this point that all gauge bosons should be massless. Certainly, this is not good because we know already from the previous slides that W and Z are very heavy. They are heavy because we see that they are short-ranged interactions. But this is what gauge invariance gives us. And then you have to introduce a second idea, which is symmetry breaking mechanism, which means that actually you kind of have now a butterfly with different wings. So it is not symmetric anymore. And this symmetry breaking mechanism is a genius counterpart, which really gives a model which otherwise would be useless because it predicts zero masses for fermions, zero masses for all gauge bosons. It gives particles their masses. And this is what is the most important, in my opinion, thing of the standard model. So in today's lecture, I'm going to give you a very qualitative explanation of the mechanism of the mass without equations. But if you want to follow math, then you can read my textbook, which is recently published, or other textbooks. So choose to your level what you find more appropriate. So and now I'm going to discuss a very important subject, origin of mass. But before discussing mass, I want to give you 6 different definitions of mass. Because this term is something we are that much used that we are almost never asking ourselves that if there is any profound meaning of this term. Let me now show you that actually the mass is something very much not a simple question. So the first definition, I think, is known to everyone. This is just inertial mass. So this is a measure of resistance to acceleration. This is just a classical definition from school. Then there is an object which I would call here active gravitational mass. This is the strength of gravitational field which is produced by a body. So, and this is completely different story in principle. So it should not be any relation to the inertial mass. So this is something related to the energy. Then there is passive gravitational mass. When you have a gravitational field and you have a body, and you look how this gravitational field acts on this body, and this force which this body is experienced is proportional to the passive gravitational mass, which should not be, in principle, the same as active gravitational mass, which is producing this gravitational field. Then there is another thing. This is the rest energy. When a particle or any body with certain mass has an energy when it is at rest. So energy equals to mc squared. Then there is a source of space-time curvature and the role of mass in general relativity. And finally, there is a quantum mass. This is a quantity which is inversely proportional to the Compton wavelength. So something which appears in quantum equations. So quantum physics, at least, is completely detached from gravity, and therefore all the concepts like masses and so on, even if you call them mass, they are completely different in general. But the remarkable thing is that experiments show that all these masses are equal to each other, and nobody knows why. But this is an experimental fact that all these things, which in principle should look completely different, they are either the same or proportional to one another. And now I'm going to discuss a secret origin of mass, at least in the context of particle physics. So, as I said, I'm going to give you kind of maybe unexpected to some of you picture. So I'm not going to show you equations, because usually if you open up a textbook, mass is very simply explained there. You just have a term in the Lagrangian which looks like mass, and then a textbook suggests this is the mass. That's the point. So we just put a point after that, and you don't dive inside and you don't try to understand how this happens. So we're trying here to kind of unveil this. So the modern physics suggests that masses, which we know today, appear dynamically shortly after the Big Bang, after a very tiny fraction of the second, when the universe was transformed to a new phase. So it was a phase transition. And after this phase transition, a field, a scalar field, which is known and was already many times mentioned during my lecture and other lectures, this is a so-called Higgs field, was condensed. And this condensation somehow, I will try to explain how, generated masses to particles. So before that, and if this would not happen, everything around would be massless, moving with the speed of light. And so metaphorically, if you want to give just a simple message out this lecture, we live inside a superconductor. And this is a picture, in my opinion, qualitative picture, which can explain you or give a shorter cut how you can explain the origin of mass. But before I dive into this, I just want to mention that there are two very distinct mechanisms for the generation of mass. The first one is for the gauge bosons. So when W or Z acquire masses. So this is one mechanism. And second is for fermions. This is completely different mechanism. But both of them are related to the same phenomena, that there is a scalar field which was condensed in the universe by some reason. Some of them were mentioned by Professor Gorbunov and Professor Zhizhou yesterday. So first, let me start with the mass generation of a vector boson. And a qualitative picture for that is the so-called Meissner effect. I think everyone knows this Meissner effect when you have a superconductor here. Yes, when you have a superconductor here and you place a magnet above the superconductor, then this magnet levitates, right? This is the reason, not the reason, this is the effect which is exploded in super high trains in Japan or in other countries and so on and so forth. So, and also kids like to play with this if they have the opportunity. But what is the reason for that? So first I will describe, so this is qualitatively, an external magnetic field is expelled from a superconductor. But how it happens? It happens in the following way. Actually, it is not expelled. So this is actually a very qualitative and wrong picture, because there is no force which just push out the magnetic field. What happens is that this magnetic field easily, without any problem, propagates inside the superconductor. But then it initiates a current inside the superconductor, which is a superconducting current. And every current has a magnetic field around this. And it turns out that this current produces the magnetic field which is rotating just in the opposite direction to the external field. And they just compensate each other. So in fact, inside the superconductor, you have two fields. The external one and produced by superconducting current. And these fields just almost exactly compensate each other. And this is the reason that this screening, metaphysicists call this a screening effect here, produce a levitation force. Mathematically, this is described by this equation, which is known as equation by Londons, where you have this number squared minus m gamma squared multiplied acting on the electromagnetic field. Now this electromagnetic field is the sum of two, external one and internal one which is produced. And so you just come to this equation here, where m gamma is not something you introduce by hand. This is something which is just following from right treatment of the superconductor, and it is related to the charge of a Cooper pair in the superconductor. So it is equal to the two charges of electrons, because they are pairs, multiplied by the number density of electrons in the superconductor and divided by their effective mass. So this quantity turned out to be of dimension of the mass squared. And when you solve this equation, you will find the solution which is exponentially decaying inside a superconductor. So an electromagnetic field propagates inside the superconductor, but with exponential suppression. And the rate of this exponential suppression is just given by m gamma. But I think this way around, I think you know about this effect somehow. But what is important is that a superconductor creates a very interesting situation. Now, inside of this superconductor, electromagnetic field behaves exactly like a field with a mass. So outside of that, it was just a field with zero mass, but inside the superconductor, it behaves as a massive field. And this is a key phenomena in the standard model. Actually, this is exactly the same effect in the standard model, which gives mass to gauge bosons. Here we are. So if you just do simple exercise and you consider a scalar field and calculate what kind of current this scalar field creates, usually it is not written in textbooks. As I said, it is just a single line. This is the mass. But when you make a little bit more mathematics, then you realize that actually when you have a condensed scalar field, actually it is not static. There are currents. And this current is just proportional with the sign minus to the external field which enters to this scalar field condensate. And when you plug this current into a Maxwell equation, so instead of G mu, you plug this number here, you end up with this equation, which is very, very much similar to the London's equation, which I showed you a slide earlier. Here you have nabla squared, which is a four-dimensional gradient. In the previous slide, it was three-dimensional lambda, and this is why there's sign plus here and sign minus over there. But what turns out that exactly you obtain exactly the same kind of equation where you have now a massive electromagnetic field, or any kind of field which interacts with this scalar condensate. So in this particular example, in the standard model, the mass is proportional to the charge of scalar multiplied by vacuum expectation value of the scalar field. So I hope that this example shows you that really in the standard model we are exploiting exactly the same idea, Meissner effect. This is the Meissner effect which gives the masses to gauge bosons. And last topic of my lecture is the generation of mass for fermion. This is completely different phenomena, and probably, okay, let's try to go slowly that we understand it. First, I will start with something completely outside of this. I want to remind you a physics of two coupled pendulums. This is a very simple physical exercise. So you have two pendulums which are coupled with a spring. And you want to find a solution how these two pendulums move. Oh, yeah. So let's go step by step. So you can introduce an angle, a vertical angle, which every pendulum makes with this vertical line here. For the first one, let's call this θ1, and for the second, θ2. We consider an approximation when these angles are small. Then the equations are much simpler. Then when you just you can do this in whatever way you want. You can try to construct forces and write the equation, Newtonian equation with forces. A more clever way would be to write a Lagrangian and then make equations of motion from the Lagrangian. Whatever way you prefer, you end up with the equation of motions. So you have a second derivative of this vector of angles, which is equal to minus d, where d is a matrix, I will explain it later, multiplied by the same vector theta. And when you plug or just make these equations, you find that this matrix D is just this matrix here, where you have, I think, very well-known object, omega 0 squared, which is g divided by L. G is acceleration constant equal to 9.81 meter per second squared, and L is the length of this pendulum. Do you recognize what is omega 0 squared? This is just a standard frequency of a single pendulum, right? Okay, certainly it should enter the game. When, for example, there is no spring, you should get just two independent pendulums. But then what happens is that to this frequency squared, you add some term which is proportional to the strength of this spring here, K. So this is just a constant from the Hooke law, divided by mass m1 of the first ball here and mass m2 of the second ball here. So you have this modification. And what is more remarkable probably is that you have also these terms, non-diagonal terms. This is just a very classical picture everyone can derive. And a way how you solve this equation, a clever way, you diagonalize this system, you introduce new angles in which this system of equation looks diagonal, and you find the solution for this new diagonal system. And when you diagonalize this, you get eigenvalues and eigenvectors. And the eigenvalues turns out to be the following. You have the frequency squared, which is just this omega 0 squared. This is one eigenvalue. It corresponds to a situation when both pendulum are oscillating in the same phase. So they are just doing this together. So this is a first normal mode. And the second normal mode with different frequency, which is higher, because you see there is this extra term here, so the frequency is higher, is when they are making anti-phase oscillation. And every other movement of these two pendulums can be described by a linear combination of these two modes. So any complicated movement is just a linear combination of that. So I'm just reminding you these very basic things so you can recognize after, on the next slides, that in the standard model we have something very similar for fermions. Yeah, so as a also useful thing, which I advise you to make your own calculation, you can find these eigenvalues and eigenvectors here. All right, so now let me go to a kind of more difficult slide. I tried to make it as simple as possible, but anyway, something we have to really think about. We are going to discuss the origin of masses for fermions in the standard model. To make the discussion simpler, I'm doing the following. I am considering just one-dimensional world where all equations become very simple. So I have one dimension in space and one time. So it's called 1 + 1. And I write a Dirac equation for the fermion field or fermion, how we call it, spinner. So now the fermion spinner can be written as two components object, which I denote here by R and L in letters. I'll explain why like that. And if there is no scalar field around, then we get this very simple system of equations. So here you have a partial derivative over time. And here we have just a constant term here, matrix multiplied by the same vector. I call these upper and low components as R and L, and there is a good reason for that. When you solve this system of equation, you can see that the matrix is diagonal, right? So by construction, the matrix is diagonal. This means that the solution will be independent. So for R component and for L component. And when you solve this, you will realize that the solution gives you just two waves, each of which is moving with the speed of light, and one is moving to the right along this axis, and the second is moving to the left. So you have these right and left moving waves. This is why they are called R and L. But there is also one more thing. I mentioned to you a few slides earlier that the standard model is constructed out of massless left chiral fields. Chirality is a kind of abstract object. If you are not familiar with this subject, probably this will just confuse you, so I'm not going to mention that. But for those of you who knows this, these R and L also are chiral objects. So they are chiral, and chirality in one dimension just coincides with a wave moving to the right or to the left. So right chiral field is just moving to the right, left chiral field is moving to the left. So before any condensate of the scalar field, you have just a fermionic field, and this field has two solutions. One is moving to the right, another is moving to the left. And they are not talking to each other at all. And each of these is moving with the speed of light. Now what happens? When you have a Higgs field which is condensed, this Higgs field produces a new matrix. Instead of this one, it produces a matrix which has non-diagonal elements. If this matrix reminds you something which we just discussed a few minutes before, I think so. It is very much similar to a matrix for the coupled pendulums. It is also a matrix of the same form. And when you diagonalize this matrix, you end up that now it has two frequencies which are just plus minus square root of p squared plus m squared. And so you can see that now you have two different solutions with frequencies in which even for zero momentum of a wave, you still have a non-zero frequency or non-zero energy. And this non-zero energy or non-zero frequency is just what we call mass. And again here, you can find that what you call a state with a mass which has a plus sign here is just a combination of these waves R and L, R plus L, when they are just oscillating in phase. And when they are just oscillating out of phase, you have another sign for the frequency, negative. So very much similar to what we just discussed for the two coupled pendulums. So these are just two normal modes. So what we call a fermion with a mass, these are just two normal modes of a coupled pendulums. Okay, and now I want to show you in some more details how this happens step by step. So let me imagine that this scalar field is not fully occupying the whole space. It just occupies a small portion of this space. So in particular, it takes this space here. And you have a right moving wave with the speed of light and left moving wave with the speed of light, which is shown by yellow. Let me just move a slider here to the left to make this field almost zero. So you have these two moving waves, one to the right, another to the left, and they do not talk to each other, and they are just moving with the speed of light. So let us see now what happens first on the animation, and then if you are interested, we can look this on equations, and the animation is based on equations apparently. But let us see what happens on the animation first. So when I'm just increasing the width of this scalar field, let me do this larger and larger, can you see what actually happens to the wave inside? Do you see that its length is increasing? Its length is increasing, energy remains the same, and this is exactly equivalent to appearance of speed, which is different from speed of light. So the momentum divided by the energy, this is the speed. So the length is increasing, so the momentum is decreasing, and therefore the speed is decreasing. So introducing this scalar field, just increasing this in space, really makes you slowing down a wave which is propagating inside this block of scalar field material. How this happens in simple words? Now let me just give you this hand-waving arguments. This is very simple. You have, let's consider what happens to the right-going wave in the presence of this block of material. The right-going wave enters this material, and now it has two different destinies. One is just continue propagating as the right-going wave, and the second is transformed to the left-going wave, so to be reflected. And so the same thing happens to initially left-going field. It also can go propagate through and can be reflected and go to the back. So each original massless wave is going back and forth in this piece of material, and the overall effect is that now you have a more slowly moving wave inside this material. Make sense, this? So you have just the probability, the possibility, which can be calculated exactly, that a wave inside this brick of material is just being reflected. And this gives you, from initially a right-moving wave, a left-moving wave. And therefore, the net effect is that none of these original waves can propagate with a certain speed. But there are two normal modes which now propagate with a given speed. So this is exactly what happens in just any transparent media. When you just take a glass of water and you have a glass and you see that the light slows down inside this water, you can also ask yourself, what is the reason why light is going slower in a transparent material? And the reason is very simple. A light, being an electromagnetic wave, produces another electromagnetic wave when they shake the electrons, atomic electrons. And this electromagnetic wave partially compensate the initial light wave. And the overall sum of these waves now moves slower and with some new angle. And very similar phenomena happens to any fermion. So a scalar field after the condensation is like a transparent media. And this is why fermions, since this media is filling the entire universe, so we live inside really this transparent media, all fermions also acquire masses. Yeah. So this is the picture. Let us now conclude. So we have two distinct mechanisms, but both of them are related to a single object, a condensate scalar field. So first mechanism is how mass is being acquired by vector bosons or gauge fields. This is very much similar, actually almost exactly, a Meissner mechanism. So the condensate behaves like a superconductor. And any gauge field which enters this superconductor is being screened. And more it interacts with this field, more screened it is. And therefore, this field becomes heavier. And you get exactly this equation with the mass which is proportional to the scalar condensate of this field. So if a field is not condensate, no mass appears. and it is proportional to the charge of interaction of this field with the scalar. And then for the fermions, this is a system of coupled chiral waves, which I just explained. So without the condensate, right and left moving waves move independently with the speed of light. And the condensate couples them. Left field now becomes a source for the right fields, and right fields become a source for the left fields. And since they are going back and forth, a stable set of waves are normal modes. And these normal modes turn out to be moving slower. This is the reason for the mass. And now let me show you just a simple animation, how these mechanisms, I will finish even earlier. Yes, how this entire structure describes us any physical process. So far we were discussing kind of deeper picture for the mass generation, but now let us discuss how neutron decays in quantum field theory. This is just an example of a decay. So you have a neutron inside the nucleus, and then neutrons is known to decay into a proton, electron, and antineutrino. And inside of a neutron, you have two down quarks and one up quark, and you remember this stack of fields, which is filling the universe. And so they are living together, coupled by strong interactions. But then around, there are also electron field and neutrino field. And sometimes they can activate this field too and release their energy. But then when they activate them, then they transform it. So one of the down quarks begin to transform its energy to the up quark, and then you have a system which is known as proton. So same fields, up and down, but then this energy goes to this field, and other part of the energy goes to another field. And then the first two fields of up and down quarks, they are still tied together by strong interactions, but other waves in field of electron and neutrino, they are just propagating out, and we see these as particles. We can detect neutrino, or we can detect an electron, or both. Okay? So this is the picture behind a quantum field theory. If you just show it visually, not with equations, but exactly the same thing happens with the equations. So, and you can calculate using Feynman diagrams in a very effective way of these processes. And so I come to my last slide. As you see, I like animation, so I call everything in this thing as code. So standard model to me is also a code. So the code runs, and the code runs as follows. So you have the local gauge symmetry, which gives you a recipe. You just replace a partial derivative by this derivative here. You have a mechanism which is called the spontaneous symmetry breaking, which gives rise to masses of gauge, some of the gauge fields, like W and Z. And you have chiral fermions. When they meet the Higgs field, they become massive because now they are kind of reflecting back and forth in this condensate. So these are the main code ingredients which is in the standard model. All the rest are just mathematical details. You can work out them, but this cannot be done in one lecture. This is typically a one-year course. So, but in order to be interested in that, I think it's worth to provide a really qualitative picture behind. So to me, the standard model is not just a list of particles. This is a consistency machine. So this is a machine or a code which produces you a very consistent result. And one of the most important of them is the way how fields do interact between each other. And this way is totally and dictated from the very first principles, from the symmetry which you just imposed, and from gauge symmetry principle. So let me stop here. Thank you very much for your attention.
Questions?
Thank you for the brilliant lecture. I want to ask, in this picture, why don't photons get masses?
It turns out that photons does not interact with this scalar field. So the mass is proportional to the charge of the field, the charge of interaction with this field. So you see, actually it is done on purpose in the standard model. You can make photon massive, but this would violate certainly, apparently, immediately the observations, right? So what we have this initial symmetry, then we have some breaking of the symmetry, but we don't break it totally. We break it still conserving one of the symmetries. So we break 3 out of 4 symmetries, and one symmetry remains unbroken. And this symmetry, this is what keeps electromagnetic field massless.
What about the boson?
And the Z boson, okay, so what happens, literally? You have a doublet of Higgs fields. Each of these fields is a complex field. So you have 4 degrees of freedom. Then you break 3 of these degrees of freedom, and 1 is intact. So these 3 degrees of freedom goes as additional degrees of freedom to 1W plus W minus and Z. And these additional degrees of freedom make these bosons massive. And a remained symmetry, which is unbroken, keeps electromagnetic field massless. This is how it happens.
It sounds a little bit unnatural.
This is, yes, it might be unnatural, but it is not occasional. This was done on purpose, how we select the breaking mechanism. We can select it in different ways. We simply can very easily break all 4, or 2 of 4, or just 1 of 4. This is our arbitrary choice. But we know that we have to end up with a theory where photon is massless. Therefore, we just select this. We can do it other way, but then we'll immediately meet a problem, right, with the data. When photon will be massive, we'll have a problem with the data. This is just done by hands.
Thank you for your lecture. And I wanted to ask first about, again, the symmetry breaking, the Higgs mechanism. So my question, first of all, just to be completely sure, when we're talking about this spontaneous symmetry breaking, we are talking about the mass in the sense of the rest energy, yeah?
Yes.
And so the main question is, if this is symmetry breaking, is there any intuitive way to explain what symmetry are we breaking by introducing this rest energy? So what is the symmetry that corresponds to zero rest energy of gauge bosons?
Yes, but this is what I just was discussing. This is Meissner effect. So the symmetry breaking is when a field, scalar field, acquires a non-zero value. And then we select arbitrarily a phase of this scalar field. And when we select one of these phases, this is a choice which we made, and this is what is breaking the symmetry in the end. Usually this is explained, if you want, in a more standard way, with this Mexican hat. You can imagine bottom of a bottle of a beer, and if you look inside, then this bottom has this shape, right? Which is not flat shape, but shape like that.
Yeah.
Do you drink beer?
No, but...
Yeah, I realized that. So if you look inside, then you have this shape. This is done on purpose in order to get less dust in beer. But then if you have a ball here, now let's imagine that this is something quantum, not a bottle of beer. If you have a ball here it has, in a gravitational field, for example, here it has a large energy, here or there it has a small energy. So now this is the bottom of the bottle, right? So it can select any point here. But once a point is selected, yes, and before, if you just ask yourself which point it will select, any point can be selected, and you have a symmetry, right? This is the azimuth symmetry for any position when ball will select. But when ball just rolls down and selects a certain point here, then the symmetry is broken. All other places are not taken by this ball, only single one. So this is what happens, and this is what is called symmetry breaking.
Okay. And the second question regarding the mechanism for fermions. So we have described this as the interaction of like left moving and right moving waves.
Right.
I'm curious if this is the reason why in the standard model the neutrinos are massless, because we have only neutrinos with we have only left neutrinos.
Yes, if you make a standard model without right neutrinos, only with left neutrinos, then they will not have mass. This is true. But as Professor Sin explained, yes, this is not the most general structure. In principle, you must add all the others. But if you want to make a qualitative picture, then it is right. If you don't put a right field, then there is no way to make the mass. Unless it is Majorana. Unless it is Majorana particle. Yes.
More questions?
Thank you for your beneficial lecture. I have two questions. The first one is, you mentioned the Mason effect, and you said that bosons get the mass due to it, and photons too. I guess no. Yes.
In principle, for the superconductor, photon also acquires mass when it is inside the superconductor, right? This is the Meissner effect. But our photons, without a superconductor, which live just in this scalar field, it could obtain the mass if it would interact with this field, but it does not interact. This is the reason why it remains massless.
What about superconductor? Can we measure this mass in superconductor, the mass of photon, or just?
Yes. So you're now talking about real superconductor, not about analogy, right? Yes. So certainly you can measure. So I showed you that the mass squared of a photon inside the superconductor is a very simple thing. So this is m gamma squared. This is the charge squared of the Cooper pair. You remember that in superconductor you have a current of Cooper pairs. So two electrons make a pair, multiplied by the number density of electrons and divided by their effective mass here. And when you have a superconductor and some electromagnetic field trying to enter this, and if we introduce here a distance r, then a probability to find at certain r the electromagnetic field is just proportional to exponential minus m gamma multiplied by r. So you can really measure this. If you just make a plot, you will get this exponential factor. You can just measure this literally.
And the second one is, you illustrated the picture with two waves going left and right. Could you explain if we have only one wave going, for example, to the right, it slows down in the scalar field, but after passing the scalar field, like light passing the, for example, a mirror, why the wave goes again with the speed of light?
Very good question. So let me come back again to the physical picture why light goes slower in a transparent medium like a glass or water.
In a scalar field. In glass, we know that there is n conceptual length. Yes, but in a scalar field, why it slows down?
Yeah, in the scalar field, it slows down by almost the same reason. So you entering field creates a new field, a new wave. Exactly like light, when goes to the transparent, light goes to water, it creates a new wave, right? Like a Huygens principle, right? And so also when you have a chiral fermion field which enters a block of the scalar field, it also creates a new wave going in the opposite direction. Let me put this in a maybe more simple way, as much simple way as possible. Imagine you just have a field which just enters this block going to the right. And then it creates another wave going to the left. Then you have inside this block two waves. One is going to the right, one is going to the left. I just try to make this picture as simple as possible, not very much realistic because there are some details, but just to give you a picture. What could happen with the sum of this wave? The sum of this wave could be still moving to the right, but much slower, right? In principle, if half of this initial wave moving to the right is transforming to the same amount moving to the right, you will end up with just standing wave. It will not move not to the right, not to the left. It will be just a wave which is standing, right? And the standing wave would correspond to infinitely large mass. So since you now have a smaller proportion of this left-produced wave, then you have a wave which is moving just with some mass, not non-zero mass, because the final wave will be just slowed down, like exactly happens with light in a transparent media. If this makes sense to you?
Maybe last short question.
But why last? We had a lot of time for...
It's
No?
not a question, it's a remark on your picture when the electron charge got a kick, and you showed the picture of how the wave is detached. The picture is actually different. So you can't go like that. Here is the picture, which actually demonstrates your point even better, but there is really a condensation of electric field due to Gauss law, so you maybe should change your cartoon to support your point even better. So
No, I did not get, I mean, what was wrong with my cartoon?
no, you have like a zero measure transition between 1 over, okay.
Yes, please.
Okay. Yeah, well, here is the particle. So you have 1 over r squared here. You're moving, right?
Yes.
Then you have like 1 over r2 square here. But the transition, it doesn't just surface. It's like it goes like this, the transition. So and here the electric field is very well condensed, and inside this region, which has non-zero measure in a 3D space, it falls like 1 over r, which actually there is in orange. You have like a finite thickness, but the electric field is going like maybe a little bit different, but like something like this.
Yes, I agree, but...
that's just a remark.
Yeah, but I know this picture, and this is exactly what is shown here. Maybe it's hard to see, but all this has this small wiggle like you just expect.
Okay.
Yes,
So,
it is.
but maybe for a student.
Yes, you are right. So if we have this field here, which goes like that, and then you have, let us move this to this point here, and this point corresponds to already a relativistic charge. So here you have really arrows like that. And here the same four arrows now look like that because of the relativistic effect, right? So electric field is becoming more orthogonal to the direction of movement.
It's even in the non-relativistic limit.
Yes, but here it's more remarkable. And then you just try to connect each of this error with each of this error.
Right.
And this is what makes you this thin layer here.
Yeah.
Yes. So this is, I think, what you have in mind. So it should be like that. Yes.
Yeah, exactly.
Yes. Yeah, certainly. This is, thanks for this comment. This is exactly what is shown on this cartoon, but here it is certainly exaggerated. Actually, this kink is less pronounced.
Okay, I think we
Yes, if we are running out of time, certainly we should stop.
Don't worry, my lecture will take less time.
okay. So we have time for more questions.
Maybe it's not a good idea.
Thank you for your lecture. I want to continue a question about photon zero mass. As I understand, at the start in the model, standard model, we have just 4 boson fields.
Right.
Not Z, W, and
Right, right.
and only after symmetry breaking, we construct a linear composition of them and choose this linear composition such that one field has zero mass. So my question is, can we, in theory, just choose another linear composition and then work in this strange theory
Certainly.
purpose?
Yes. If you want to make your calculation just more difficult, you can do this. This is
So it's just a convention.
just convention. So this is exactly what happens to the system of coupled oscillators or whatsoever. You can work out with a non-diagonal system of equations. You can still solve them, for example, numerically, right? Numerically, it doesn't matter what is inside. But if you want to solve them analytically, it's much clearer and much easier just to diagonalize this first and then find the normal solutions.
So I will have 4 non-zero mass fields.
Right. But with complicated interactions between them, yes, which will mimic exactly. This is exactly what happens when one massless field creates another massless field, but the overall net effect is like it is a massive single field, right? But you can work with massless fields too.
Can I ask you some maybe comments, maybe a question? Can you explain why you used local transformation, phase transformation? The reason why you don't one you did not confine only where alpha is not a function of x but is a constant phase. Why you need? What is the reason that you should?
Okay, I got your question. Yes. Yes. So if you want to get a kind of a physical answer, why do we need gauge transformation, right? Why we need this? Then the answer is very simple. There is no physics behind the gauge transformation, just zero physics. This is just a principle which finally can be wrong. So gauge invariance is just a principle which we found really brilliant because it can predict us new interactions. And so far we were very successful because it gave us 2 very successful theories. One is the electroweak theory and another is quantum chromodynamics. Both are based on the same gauge invariance principle. But as a matter of any principle, it cannot be deduced from something else. So principle is something which you formulate or you postulate, and finally you can end up with the situation when it does not work. For example, closer to you maybe. Imagine that someone has a principle not to pay for the bus ticket. It might work unless you meet somebody who punishes you for that, right? But before that, this is your working principle and you live with this. So this is exactly the same situation. Creating a principle of gauge invariance is something like not paying for the bus ticket, and there is no real reason, physical reason behind that. What I gave here, it was kind of qualitative picture with this free friends story, which kind of should drive you to the idea that it may be a good idea, because otherwise even a free theory would not work. But I don't know if you buy these arguments or not.
Maybe last question.
Thank you for the lecture. I have one question that remained with me from yesterday, and today I still can, I guess, ask it. You said that all fields, well, at least all that we discussed, are just bosons interacting with fermions. Is that right?
Yes.
Is gravitational field also can be described in this model?
Well, in principle, yes, but it turns out that a quantum theory of gravitational field is just mathematically ill-poisoned, so far at least. But in principle, you can make exactly the same approach. You can also create a quantum field theory without going into deep details for a spin 2 particle. So far we are considering 0 spin, 1/2, and 1 for gauge boson. You can create this for the spin 2 particle, and you will find, based on these simple arguments, that it will produce a universal attraction. Whatever other particles are interacting, exchanging by this gravitational or spin 2 particle, it will be attracting force. But then if you go into details, then you will find that the theory, at least in its simple form, will be mathematically ill-poisoned.
So, as far as I understand, now gravitational field just exists without any...
Right now we have just classical theory. It is the situation. We don't have a good quantum gravity theory. Unless, okay, we don't discuss here like theories like quantum loop gravity and so on, which kind of trying to reproduce this, but we don't have as a routine theory, we don't have quantum gravity so far. This is a problem. I mean, nobody can construct it.